This video will demonstrate the ILASP system being applied on an event detection task, in which the goal is to identify pairs of people who are meeting in a video stream. In general, machine learning systems are very good at extracting patterns from data, enabling them to learn to make predictions and classifications on new data in the future. They've been successfully applied to many real-world problems, such as image classification, machine translation, and automated decision-making. Many of the leading techniques for machine learning have several major drawbacks, including an inability to generalize from small amounts of data, which can mean that huge data sets are needed to train the system. This is both expensive and, depending on the problem domain, might require a level of expertise. A difficulty incorporating existing knowledge. As humans, we're very good at this. We often extend our existing knowledge by using a combination of concepts that we've learned previously in order to explain a new concept. Many machine learning systems are incapable of incorporating existing knowledge, meaning that they must instead learn everything from scratch. A lack of explainability. Many systems learn models which are not easily interpretable, even by experts in the field. This means that it is often very difficult to generate an explanation for the model's decisions, which is especially problematic if the learned model makes a mistake. On the other hand, logic-based machine learning systems, which combine machine learning with techniques from the field of knowledge representation, can generalize from relatively few examples, and they are able to incorporate existing background knowledge in the form of logical rules. What's more, because the learned knowledge is also expressed using logical rules, it can be easily translated into plain English, making it possible to explain what has been learned. The learned rules can also be used to generate explanations. In this video, we show the ILASP system for logic-based machine learning being applied on a series of video clips in which each frame has been annotated with the locations and activities of various people in the frame. We are using ILASP to learn a set of rules which describe the conditions under which a meeting between two people starts and ends. The first step is to transform each consecutive pair of frames into an example for ILASP. Each ILASP example is generated from a pair of people present in the frames. In this case, we're using the people marked as blue and green. The ILASP example contains their activity annotations, walking and active, the distance between them, 38 pixels in the first frame and 41 in the second, and the fact that they have been labelled as meeting in the first frame and not meeting in the second. As humans, we know that if an event is occurring at one time point but not the next, it must have terminated in between the two time points. Similarly, if an event holds at one time point but not the previous time point, it must have been initiated at some point in between the two. We encode this general knowledge as a set of logical rules which are used by ILASP. When ILASP is run, it attempts to find a set of logical rules that explain the meetings taking place in the given examples. In doing so, it balances trying to explain as many examples as possible with trying to minimize the size of the learned solution. This balancing is crucial to prevent overfitting on the training data. ILASP uses an iterative approach, and in each iteration finds the best set of rules using what it knows so far. It predicts what it thinks is the score of the rules, where the score is a measure of the quality of the rules in terms of their size and the number of examples which ILASP thinks that they explain. In early iterations, the prediction of the score will be much lower than the actual score, because there will be lots of examples that ILASP thinks are explained that are in fact not explained. ILASP picks one of these examples and uses it to learn. On the screen, we can see the rules that ILASP learns in each iteration, translated into plain English. We can also see ILASP's predicted score and the actual score. The error is the difference between the two scores. This error is plotted on the graph at the bottom of the screen. We can see that the error converges to zero as the iterations increase. When it reaches zero, the rules are guaranteed to be optimal, meaning that they have the best score possible within the search space. Once these rules have been learned, they can be used to detect meetings in new clips, generating explanations each time a meeting is detected. Because the rules are expressed in English, they can also be easily explained to non-experts. This video has shown ILASP being applied on an event detection dataset and has highlighted 3 of the main advantages of logic-based systems over other forms of machine learning.